Hello everyone, welcome to this recording on Norton equivalent circuits. So this example requests us to determine the Norton equivalent with respect to terminals A, B for the circuit below. First thing to note here, this is a circuit that has only independent sources. So similar to the problems that we were doing in the Thevenin equivalent, we'll be following the same procedures. We'll have to deactivate when we're determining Rn or Rth, and then we'll have to apply the theory that we've picked up for the In that we need to calculate. So the first part here would then be to determine your Rn. Remember, when they talk about the Norton equivalent, you are expected to determine the Norton equivalent current as well as the Norton equivalent resistance, such that you have a final circuit that will look as follows. You're going to have your Norton equivalent current, you're going to have your Norton equivalent resistance, and you would then have your terminals A and B, which you could then collect your load. So this is the destination, this is where we're going. So the first part of this, we're going to first determine the Norton equivalent resistance. So I'm quickly going to take a copy of this diagram and paste it. Right, so what do we need to do? We need to determine the equivalent resistance looking into the load terminals, and for us to be able to do that, we know that we need to deactivate our sources. So we know that the current source must become an open circuit and the voltage source must be replaced with a short circuit. So if we redraw this, we then will have a circuit that will look as follows. And these will be our terminals A and B, and that will be the open circuited terminals. Now we need to determine the equivalent resistance with respect to these terminals A and B. Right, so we should be able to see from that we are going to have to calculate the equivalent resistance. Just getting the calculator out. Right, so what is the connection between, we'll start from the left hand side. If I have a current going in here, it will split as follows. So we should be able to see that the 6 and the 5 ohm are connected in parallel. They share two common nodes, and that's your one node, and this is your other node. So Rn is going to give me 5 in parallel with 6. Once we have this combination, that parallel combination, it will be in series with the 5 ohm resistor, so we'll say plus 5. And once we have this combination, it must be in parallel with the 10 ohm resistor. That will be the value of the Norton equivalent. So we first determine 6 in parallel with 5. So 6 in parallel with 5 is going to give us a value of 2.72 ohms. So that gives us 2.72 plus 5 in parallel with 10, which is going to be 7.72 in parallel with 10. And we can get that final value. So plus 5 gives us 7.72 that in parallel with 10, we invert that, that will give us a value of 4.35 ohms. We can just double check that again. 7.72 in parallel with 10 gives us a value of 4.35 ohms. Therefore, Rn is going to give me 4.35 ohms. That's the first part of this problem. So the next question requests for us to determine In, which we know is the Norton equivalent current. How do we get the Norton equivalent current? We know that the Norton equivalent current is the maximum current over the load resistor, and in order for us to get maximum current, we need to replace the load resistor with a short circuit. So we replace it with a short circuit, and we should be able to see that by replacing the load with a short circuit, there will be a cancellation of the 10 ohm resistor, because the current flowing in the circuit will bypass the 10 ohm resistor and flow through the short circuit. So the simplified circuit that we have is the one that we see in blue, and we can now do a KCL in node V, and we can do a KCL also in this node. Let's call it node I. We can also do a KCL. So in node V, we will say that the current going in, which is 15 minus V over 5, is equals to the current going out, which is 2 plus V minus 0 over 6 plus V minus 0 over 5. Right, and we can use this equation to determine the value of V. So 15 minus the unknown over 5 becomes 2 plus the unknown over 6 plus the unknown over 5. Right, and we get a value of 1.76. Right, so V is equals to 1.76. Now how do we find In? We can do KCL at node I, where we're going to say 2 amps plus V minus 0 over 5 is going to give us In. So that's going to be 2 plus 1.76 divided by 5 should give us In. Right, and that gives us a final answer of 2.35 amps. So In is equals to 2.35 amps. And eventually, or the final diagram that we should be drawing out is going to be a diagram that's going to have a current, it's going to have current value of 2.35 amps. It's going to have our resistance that we've calculated from the previous circuit, which is RTH, and the open circuit where the load would have been connected. Thank you for watching this video and enjoy the course.